Hello everyone, welcome to another video from Advanced Math Tutors. Today I wanted to bring you a video on U-Substitution. And U-Substitution is one of several integration techniques that I will be showing you. And U-Substitution is the first one. So the way I want to present it is, let's say I want to take the derivative of a function like this. So I have the derivative of sine of x squared. And the reason I chose sine of x squared is because in order to take the derivative of it, I'm going to have to use the chain rule. And we remember how to do this. This is equal to 2x, that's the derivative of the inside, times cosine of x squared, since cosine is the derivative of sine. And now, what if I gave you the opposite question? Let's say I wanted you to integrate 2x times cosine of x squared dx. Well, you might say, well, I know that the derivative of sine of x squared is that function, so by the fundamental theorem of calculus, the integral of this function must be equal to sine of x squared. And you would be right, except what if you didn't know that the derivative of sine of x squared was this function? How would you evaluate it? And this is where U-substitution comes into play. And the key is to recognize here that you have an x squared here and its derivative. And whenever you see something like that in an integral, you should think to yourself, all right, I can probably use U-substitution in this problem. And so the way I would evaluate this problem is I would set u equal to x squared. And now by implicit differentiation, du must be equal to 2x dx. And so now, by doing this, we can rewrite this integral in terms of u, and hopefully it'll make the integration easier. Because right now, we have really no way of integrating a function times a function. Just like with derivatives, the derivative of f times g is not the derivative of f times the derivative of g. So here we can't just integrate both functions separately. We have to find a different way. And that's this U-substitution here. So why don't we rewrite this integral in terms of u. So now u goes in for x squared, and then we can replace this 2x dx with du. And so now what we have is the integral of, so 2x dx is just du, so that comes out. And now cosine of x squared, remember x squared is equal to u, so therefore cosine of x squared must be cosine of u du. And now you may think, well, how do I evaluate an integral in terms of u? Is it any different from evaluating an integral in terms of x? And the answer is no. The integral of cosine u du is equal to exactly what you might think, sine of u, because it doesn't matter what the variable you integrate. Like this could be the integral of cosine of smiley face, d smiley face. And when you integrate this, the answer will be sine of smiley face plus c, of course. So we are going to add this plus c. But it doesn't matter, except now what we can do is we can substitute back in for u. Remember, u is equal to x squared, so we can put that in. And now we get that this is all equal to sine of, remember u is equal to x squared, so x squared is an inside, plus c. And remember with the original function that I took the derivative of, it was indeed sine of x squared. And so this is just proof that this integration technique is worth diving into. And essentially what U-substitution does is it aims to undo the chain rule of the derivative. And so my advice to you would be, if ever you see an integral and inside the integral you have a function of x and its derivative, then go ahead and make a U-substitution, any U-substitution. You could, like, in this case, I could have said u is equal to cosine of x squared. I could have made this substitution, but that's not what would have been of use to me because I don't have the derivative of cosine of x squared. But you should always make a substitution and see if it makes the integral better. In the next video, I'll give you some more examples because U-substitution definitely takes some time getting used to and recognizing its patterns. And so that'll be for the next video. Don't forget to like and subscribe.